A very good evening to all the respected speakers, faculty members, researchers, and participants. On behalf of the North Cap University and the organizing committee, we warmly welcome you to day 6 of the ATAL Online Faculty Development Program.
Hi Devika.
And I, Kashvi.
Sincerely thank you for your continued participation and engagement throughout this program. Each day has taken us deeper into the evolving semiconductor ecosystem, and today marks another important milestone in that journey.
The session scheduled for today focuses on energy efficient circuit design, global semiconductor market dynamics, and industry trends shaping the future of semiconductors. Together, these topics bridge core VLSI design concepts with policy, market forces, and real world industry perspectives.
From understanding high speed energy efficient data converters to gaining insights into the global semiconductor boom and future industry outlook, today's session aimed to provide both technical depth and strategic awareness.
It is now our privilege to welcome our first speaker for the day, Dr. Hitesh Rimalli, for session 11.
Dr. Srimali is a professor at the Indian Institute of Technology, Mandi, in the School of Computing Electrical Engineering. He holds a BE from Nirma Institute of Technology, an MTech from IIT Kharagpur, and a PhD from IIT Delhi, reflecting a strong academic foundation from premium institutes.
He brings a rare blend of academic, industrial, and international research experience. He has worked as a senior designer at ST Microelectronics and later as a postdoctoral researcher at the University of Milan with association at IFN Italy.
His research interests span analog and mixed signal VLSI design, energy efficient data converters, radiant hardened circuits, ADCs, and on chip instrumentation, making his work highly relevant to high speed and high reliability applications.
Dr. Srimali will now deliver his session on energy efficient data converters for high speed applications. This session will focus on design challenges, architectural choices, and power performance trade off in modern high speed data converters.
Participants are requested to post their questions in the chat box. The Q&A session will be taken at the end. With this, we invite Dr. Hitesh Srimali to begin his session.
So my screen is visible?
Yes,
Yes,
sir.
sir.
Hello. Okay. So thank you for the introduction. So we are going to talk about the energy efficient data converters for high speed applications as it is given into that. But before that, I'll start with a bit about from where we are coming from. So it's IIT Mandi, which is on the Kaman Valley near to Mandi city. It has actually two different campuses. One is known as the North Campus, one is known as the South Campus. So you can see here, one is South Campus and one is North Campus. Beside, like uh, two sides of one mountain, and in between also we have developed many things. But this photograph was taken almost 10 years back. So thereafter, lots of things happen, right? So this is our North Campus where all UG studies are happening, and all the UG students are also staying here, and both side equal number of students are there, and mostly all UG courses lectures are happening here in north side, whereas south is actually for research students, and also it caters one of the laboratory known as the Center for Design and Fabrication, which is one of the one of the facility available in country with class 100 clean room facility. So it's a very good facility in that, which is on the river of in the bank of river Ul. We have all the good facilities which are required. Sometimes, of course, it's snowing also, and of course, it's a very good place to study, very good place to have your research. Yeah. So this was about our campus, and in VLSI, there are various areas are there in IIT Mandi, having very large pool of VLSI faculties, and these areas includes analog mixed signal VLSI area that's taken care by me. Then the RFIC design, micro engineering. Then we have device fabrication, modeling, characterization, advanced lithography, solar cell, NVM, DFT plus quantum, transport, neuromorphic computing, And on digital VLSI side also, we have very good number of people. We also have expertise on semiconductor materials, and also like AMOLED displays. So in a way, we have variety of people which caters the requirement of all the requirements of VLSI design and VLSI technology. Going further towards our understanding, but before that, this is my group where I'm working on various things like radiation hardened circuits, where I work on particle detector and PAT scanner. I also work on signal and power integrity, known as the SIPI techniques for circuit analysis, for jitter analysis. And of course, I work on data converters with different applications, such as space applications or maybe biomedical applications. And currently, I'm also working on chip scale atomic clock, which involves understanding and design of PLL. So that is what we are doing it. So let's start with our work. So if you look at a general transceiver architecture, you can see that most of the time, like there are two major things are there. One side is analog signal processing, one side is digital signal processing. So that converts analog signal into digital bits. If you look at here in between these two sides, it's ADC and DAC. So one is analog to digital converter and another side is digital to analog converter. And this is the most important block. I don't say that others are not important, but this is one of the important block where it creates sometimes bottleneck, because number of bits are creating lots of problems. Sometimes you want more number of bits, and of course more number of bits are good, but because of technology, because of many constraints like noise and non-linearities, you might not achieve the required number of bits. And also, like, it's not only about the number of bits, it's also about how many what will the frequency of operation. When you are going with that, it has to be like synchronized with frequency synthesizer, which is also known as PLL. And like quantization by comparator circuitry, all these things where you need very high input offset voltage. And of course, when you are converting this code, it's always look like it's a digital, but those are not always digital. Sometimes you have variety of codes are coming which needs to be converted to binary, or maybe you have to deal with whatever the code you are dealing with, you have to work on that. So when you are selecting an ADC architecture, you have to see like these three things. These are the primarily three specifications which you need to see. But other than that, there are many other things are also there. Like if you are saying that you are designing an ADC, whether it's good or bad, how to know that? So there is always actually trade-off between these three. And from there is one important term known as the figure of merit, and given by Walden. Walden was a scientist who was giving this way to evaluate an ADC. It says that power consumption divided by 2 raised to E knob times Fs. Fs is the sampling frequency. E knob is the effective number of beats. Right? And FOM is figure of merit. So if you can achieve this as low as possible, then you are a good designer, or your ADC is a good design. It's measured in something like joule per conversion step. If you look at these dimensions, it will be joule per conversion step, and you have to achieve as low as possible. And also I call this one as energy efficiency. Right? So you have to achieve very good energy efficiency. When this FOM number is coming low, means your ADC is good. There are a variety of ADCs are available in the market, like flash ADC, SAR ADC, pipeline, and one more is actually creating lots of impact in recent years, known as hybrid ADC, which is combination of two ADC, sometimes three ADC, or maybe different algorithms which are being, uh, you know, which are actually connected together, and then you are designing your ADC. Now let's look at some of the numbers, because those are very important. But through a literature survey, we need to check it. Generally, the best journal or the best conference in this particular field is ISSCC is the best conference, and JSSC is actually the best journal of IEEE. Both are very good, and that's why like all the comparison and everything has been done with ISSCC and JSSC, right? So if you look at that and you read some of the sentence like convergent energy, now the important part is it's not about just energy efficiency with respect to conversion step, but one more important parameter which is playing the role over here, which is known as conversion speed. Now conversion speed is measured in terms of number of cycles, number of clock cycles. Note that for different structure, you will have different conversion speed. So you want your answer to be coming as soon as possible with low energy, right? So this is what our agenda. The conversion speed means number of clocks has to be as little as possible, excluding, when we are saying number of clocks, we are excluding two clocks which are sampling and one is end of conversion. So two clocks are there. So we are excluding those, and then we are talking about the number of clock cycles because you can't get rid of this sampling and end of conversion cycle. So this conversion energy of ADC is reduced by half every 2 years. So this is taken from one of the professors from Stanford, Professor Murmun. So he wrote in his paper that conversion speed is actually reduced by half every 2 years. Speed of conversion increases by 2 folds every 4 years. Now, if you wish to have 20 GS per S, means giga samples per second ADC with a power dissipation of 1.2 watt. Look, you might be thinking in chip design, how much will be the big power you can have? So that big power is actually what, if you are in giga, of course you can't get rid of what will be there. It will consume lots of power because this is the science, right? If you are increasing the frequency, your power has to be burned. And if you look at the Ethernet standards, so 100 GSPS, if you want to design, you can also have 4 times interleaved 25 GSPS ADCs, and the best number of bits you can achieve at this frequency is around 5 to 6 ENOP, right? And for the long range, like when you have the 2 times interleaved 50 GSPS, then also like you can have 5 to 6 ENOP. So as you are increasing the number of your bandwidth or the conversion speed, the achievable number of bits are not too much. It's actually in the range of something like 5 to 6 bits, right? So this is just for your information and to understand that which numbers we are talking about. So time interleaved and multi-bit processing can lead to have the better efficiency. This is first of all the easiest way till date. Wherever we require, we want to achieve the higher number in terms of conversion cycle. Let's say 100 GSPS or better number. You are just taking the interleaved structure and keep them in parallel with different clock cycles. Then you can have the high speed. So this is a well-known technique known as the TI ADCs, means time interleaved ADCs are most popular architecture that satisfy multi-GSPS and high resolution requirement as well, right? And SAR ADCs are superior in this aspect of power efficiency and are highly scalable to an advanced CMOS technology. So SAR ADC is the popular one taken out from this paper, right? And in some of the paper like SAR ADC designed for 5 GSPS with 10 bits resolution consumes around 76 milliwatt of power. So with some techniques and technique of time interleaved and other techniques, they have achieved some number which is coming in the lower range. So you can understand like he achieved in 76 milliwatt. Earlier it was 20 GSPS and that was consuming something like watt. So that way we are actually reducing the power here. But this is time interleaved. That's why it's being happened. And we are not studying right now that paper, but I'll tell you some different scheme through which you can achieve even lower power. So now, as I told you, like the best conference in this field is ISSCC, IEEE ISSCC. So, and the same Walden's FOM, which is equal to power divided by 2 raised to e knob time Fs. So it's checked with 97 to 2021, and for as you are increasing the bandwidth, the figure of merit or the energy efficiency is actually shoot up, right? Look at this. This is a logarithmic scale, so it's actually increasing exponentially, right? So it's a very alarming, time when it's you're going in high frequency side or you are above gigahertz. So gigahertz is actually the challenging one, and one has to look at that very carefully. Other thing is that if you are increasing the bandwidth, the enorm which can be achieved is actually reducing. You just look at that even with different architecture like flash ADC, SAR ADC, delta sigma, or maybe pipeline. You just look at that, the best achievable number is actually because of flash. You know that flash ADC is taking, you know, lots of area if you have more number of bits, right? So you need to have more comparators, more, and more comparators means more energy. And if you look at the SAR ADC, SAR ADC is everywhere. It's visible everywhere, right? Because it's the red color. And of course, this delta sigma ADC is also one of the popular at the low frequency regime. In between, like moderately high or high frequency regime, pipeline ADC is also playing important role, right? So now let's go with the another background that analog to digital converter plays an important role in the design of RF transceiver architecture. So we are talking in terms of gigahertz of frequency, right? And hybrid ADC architecture is the one which has combination of two architectures which exhibit excellent performance for analog and mixed signal system. The hybrid is the one which we are going to take, and we are going to study that. As we learn from the Murmur's paper, this SAR ADC is one of the best, or the best one to achieve, the good number of bits at medium speed. And the bad part, you can say bad part or good part. Bad part is that it takes n number of clock cycles. So if you want to design 10 bits of ADC, you require 10 clock cycles to get the conversion. Means if I want to design something at 100 MSPS, means this is the speed, and if I want 10 bits, then actually the convergence for this, we need to design the whole thing at 1 gigahertz, because everything has to be 10 times faster over here, because it takes so much of cycle, right? And divide by 10 gives you 100 MSPS, right? And we are not including sampling clock and end of conversion clock. If you add them, then it will be 12. Whereas the flash ADC is one of the popular one for the low number of bits. You might be knowing in single clock cycle you have the output, but it consumes lots of power. It's a higher bandwidth, higher power consumption, and number of bits are very less, right? You cannot go, let's say, 10 bits of ADC using flash architecture. If you want that, then it requires at least 1023 comparators, right? And each one of them are burning the power in parallel. So that's again sometimes not advisable, but taking the advantage of one architecture and adding same in another architecture, you can have the advantage of both. So I'm planning to tell you how you can add both of them, and that was one of my PhD students work which he did it, and that journey I'm going to tell you. So now again, uh, other than those, there are many bandwidth enhancement techniques are there. Like you can have the time interleaving that we already learned. This is from ancient time. Many people are doing, including the Chandra Kasan's paper. It is there, right? And you can see that other than that, also like alternating comparators, multi-channel ADC techniques, many things are there, which has to take care of following non-ideal effects also, like offset cancellation, kickback noise, all these things needs to be taken to achieve very high energy efficiency. And when we are saying high energy efficiency, it's figure of merit in power divided by 2 raised to E naught times Fs, right? So now let's go slowly on flash architecture, because my proposal to add the flash plus, so our proposal to add the flash plus SAR, I want to combine both of them and to get the advantage of both of them together, so that I can achieve very good FOM, or you can say that energy efficiency. This is what my agenda is. So let's recap the flash architecture. You require 2 raised to n minus 1 number of comparators. Everything is happening in parallel. Of course, the output is coming in not in binary form. You have to have the thermometric code which needs to be converted to binary. Means you can use the encoder and you can have the data storage register, and you can have the output, right? So this is what in general structure is there for flash, but this is very high power consuming architecture, but it's very fast. This is the fastest one. There is no doubt about this. This can achieve the highest speed, right? Because everything is happening in parallel, right? Now let's look at the SAR architecture. So SAR architecture is the actually using binary search algorithm. It's also used from ages by many people. This is actually not parallel processing, but it's a serial processing. Each clock cycle, like internal clock cycle, so there are two ways. Like the sample and hold is actually taking the clock at every conversion speed. So conversion speed is here. That's the frequency of this sample and hold. Whereas in this entire structure, the conversion speed divided by the number of bits, right? Because this particular structure will run for at least n time iteration. If you want to have the number of bits, you have to wait for n number of clock cycle. So there are n iterations are required to achieve the required number of bits. Means conversion speed is n, excluding sampling and end of conversion cycles, right? So because of that only, like, you can achieve medium speed. Let's understand one more thing, like achieve designing something at gigahertz is consuming lots of power. That also we learn it at the beginning. If you are going with no technique, then having a design of comparator, let's say this comparator at gigahertz might be very difficult. Let's look at that how it works. Like if I want to have the speed of conversion speed of 1 MSPS and number of bits are 10, then I need to make this whole thing working at 10 megahertz, and all the components like comparator, DAX, and other resistors and everything has to be much faster than 10 megahertz. So this is achievable. If we do 10 mega samples per second and 10 cycles, still 100 megahertz might be achievable. But if you're going, or if you're ready to have, let's say, 1 GSPS and having 10 cycles, you require everything to be much faster than 10 GSPS, and 10 GSPS is actually equal to watts of power, right? In like I'm talking about technology, anything below 130 nanometer, you will have watts of power, because that's a science. You can't, challenge that if you're going with the regular techniques. So this might be hardware efficient and can achieve the required conversion cycles if you are keeping everything at the medium speed, let's say 100 megahertz. But note that when we are seeing this ADC is working at 100 MSPS, means for given number of bits, you have to make the things much faster than the conversion speed. So it is required on the required number of clock cycles, or it's exactly n number of clock cycles. Note that many other structures are there, like integrating type ADC, which requires 2 raised to n number of clock cycles. So we are not talking about it, and that structure is pretty slow. It works for the sensors application, whereas for the transceiver applications, 5G, 6G, even for that, people are using time interleaved SAR ADC, or maybe time interleaved pipeline ADC, or pipeline ADC are the popular choices. right? So one can take that, but let's understand that what are the advantages of SAR. It's pretty fast. It takes only n clock cycles to give you the answer. The only problem is you can't go beyond 100 megahertz because you have to make the whole thing, n times faster. So, so what we are proposing, or we are saying, it's also given in many good papers also, that combination of flash ADC with flash architecture with SAR architecture. So instead of having one comparator, which was the case over here, we'll have n number of clock. You have, sorry, small p number of comparators and small p number of decks, and same way, like everything has to be, actually adjusted according to how many number of architecture you are keeping in the flash. So this is what you can do. No worry, right? It's again binary search algorithm with parallel conversion of partial bit. So if I keep these comparator of 8 comparators, let's say, sorry, it's 7 comparators. If you need 7 comparators, then you can achieve 3 bits in a single go. Means after one clock, you can have 3 bits available directly. No worry. By the way, this is what you are seeing here. It's a thermometric code which has to be converted to binary to give it to successive approximation. So inside this, there is thermometric to binary code conversion is already there. So I'm not going into that, but that's part of it. You have to use it with an encoder, and whatever the digital bits are getting available, that's are having with different DAC value, which are going over here. Note that it's a thermometric code, so thermometric code will give you, only one, and maybe there is a only transition place where you are going to see 0 and 1. Other places you will see either 1 or 0, right? So that's the beauty of thermometric code, but it requires more number of bits, right? So that's also the one thing we have to take care. So let's going further. So how it works in hybrid ADC operation of flash and SAR, which will give you the start point will be the sample V on decks on different decks. So it's getting sampled over here. DACs provide the reference level to the comparators. Comparator generate the thermometric code based on the DAC. The SAR logic converts the thermometric code to binary. Yeah. Yeah.
Hitesh sir, sorry to interrupt you. So is it possible if you can share these slides with us? The signal is breaking. So, I mean, you can please continue, and once we will share, you can continue from that point. So we will share the slides for you. Is it possible? The signal, cool. Yes.
It's a pretty big file. That's why it's taking time, maybe. Anyway, it will come. Right? But are you able to see
Yeah.
my screen now?
Yeah, it's
Okay.
slightly better.
So, okay.
You may please
So this is
continue. We will share.
like, sure. So sampling phase, switching phase, and comparison phase, and you have the end of conversion phase. So we have not considered these two, sampling phase and end of conversion phase. Other than these are going to take exactly n number of clock cycles, right? That's the case of SAR. But when you have the hybrid ADC where you are generating p number of bits from this flash, and total you are expecting to have the n, then n by p number of cycles are required to generate or code, right? So earlier, for the case of simple SAR with 8, let's say 9 bits, require 9 clock cycles. If you are keeping 3 bits of flash at the end, now you require only 3 conversion cycles, right? So it will take only 3 conversion cycles. But what is major advantage over here is as follows. If you look at the previous structure was giving you one bad thing, that you require 10 times higher for running the SAR architecture, right? If you want to have the n number of like bits are 10. In this case, when you have the partial bit conversion through flash, you require n by p faster, all the elements, right? Means compare SAR, DAC, all digital structure has to be faster by n by p times. If you are interested in 3-bit version from flash side and the total is 9 bits, means you require 3 number of conversion cycles, right? And you require 3 number of conversion cycles, then all these comparator and other things which were required 9 times faster, right? Faster than your conversion speed. Now it's required only 3 times faster, right? So that gives you advantage. Earlier it was difficult to achieve the required things because the number of iteration and number of things were taking, asking you to make the faster system internally. Now that's not required. You can make the slower system and which can consume lower power, and effectively the overall thing will be you will have the better energy efficiency than the previous one, right? It's also visible from our basic sense that it should consume a lower power. Now, of course, the number of components have been increased for sure. These comparators and DACs have been increased for sure, but that we have to keep it in our mind, and how to trade off and how to get the things better. We can look at that. So there are various research possibilities. When we started, we just looked at that accordingly. That one can make the DAC optimization, one can make the better comparator, one can make the very good clock optimization, and one can make the sub optimization, and everything together one can make a hybrid architecture optimization. So I'll try to cover as much I can for this given time. So let's start with the first comparator optimization. But before going that, it's important that when you are going to have this data and clock together, you have to have the sync of delay. So that is generally does by or being done by all the designers. Let's look at that how to make this comparator. Okay, so this is again before going to that, there is an important thing which I was talking about, that how many number of bits you can take it partially over here, number of bits p. So we just check the mathematically for our structure that we are designing, that if you are taking 1 bit per cycle, means this is normal SAR, this is the equivalent of normal SAR. If you have 1.5 bits, 2 bits, 2.5 bits, again this is knob at the hello. Okay, okay, okay. Now you should be able to see that, right? Are you able to see my screen, right? Hello? Hello?
Yes, sir.
Yeah, yeah,
It
okay.
is a
Then
little
fine.
blurry,
Okay.
but we can see your screen.
Okay, okay. Anyway, so the number of bits means enob at the flash side. You can have, you know, the minimum number which you can have is actually 3. If you have 3 number of bits at the front side of flash, then there is no problem. But beyond this 3 bits of cycle, we found out that that number is actually pretty big, right? And the number of required DACs, number of ADCs has been kept over here, and this is coming from how much energy is required. So that has been found out mathematically, and that has been plotted over here. So 3 was one of the actually number where you can achieve good energy efficiency at the low good energy efficiency at lesser number of components, right? Okay, so now let's go further for having ADC specifications which we want to design. Like so this has been designed in 28 nanometer CMOS technology with the power supply of 0.9 volts. The architecture is hybrid. Speed is 1 GSPS. Algorithm is 3 bits per cycle, means you have 3 bits of flash ADC, and of course total resolution 6 bits. So you require only 2 number of clock cycles, right? Excluding sampling and end of conversion. And as per our calculation, we wanted to have something like power consumption to be 2.33 milliwatt. These numbers are coming mathematically, okay, and we try to match it, right? So going further for those numbers, when we want to have the 1 GSPS of requirement, of course, 2 clocks or that's a conversion cycle. And if I'm adding sampling cycle as well as end of conversion cycle, right? So total, actually it requires 4 clock cycles. So I need to make the overall system to be faster by 4 times. Means I need to have 4 gigahertz of comparator. Accordingly, you can find out the resolution also, and resolution will be around 14 milliwatt volt by you have to divide 2 raised to 9 by 2 raised to 6, and still it will be divided by half because it's a half LSB resolution we have to achieve. So that's why like this will give me around 14 milliwatt, and you can also have the decision time with 94 picosecond. This has been designed for around 7 time constant, and similarly like all these things have been calculated on paper, digital logic and other things to be working on given given value of speed. Other than that, you must be using a DAC, because DAC is important thing over here. If you are using a regular char scale DAC or maybe other DACs, that might give you problem, because let's understand one important phenomena over here. If you are going from, let's say, if this is 0 and VDD, its equivalent digital code will be all 1, and for 0 all 0, and exactly at VDD by 2, if you look at this VDD by 2, at VDD by 2 this will become 1 and rest of them are 0, and exactly VDD by 2 plus delta LSB or 1 LSB, you're going to have 0 and all 1. So there is a big transition over here which is happening just nearby VDD by 2, which can impact your overall INL, right? Integral non-linearity will be increasing, so one has to take care of it. And the solution of that is you can use the segmented, right? You can use the segmented split capacitor DAC. So that has been decided, and accordingly all these things have been found out in terms of resolution, speed, and unit capacitance has been found out by KT by C noise, which has to be much lower than half LSB, and through that the settling time and other things have been found out, and that has been kept over here for the design. So that is one side. Let's go to the inverter side, where inverter, the comparator, if we're calling that word as inverter, what we are saying is if you are going to make the comparator, normal comparator, the problem is it's going to consume a lots of power, because this comparator we are going to design at 4 gigahertz, and 4 gigahertz is actually not a good choice, right? So 4 gigahertz means it is going to have lots of the problem in terms of power. So what we are proposing, unfortunately, what we thought like as this structure that has been actually patented. So, but that idea we got it during this time, that you can use inverter as a comparator. What exactly inverter does? Inverter says that if everything is fine, like that switching threshold is exactly VDD by 2. So there is a transition. I made it wrong way. It has to be. So this is V in and V out, right? So if your V in is increasing from 0 to VDD, exactly at VDD by 2. Note that this is happening only when you have designed this with the fact that both the resistances are exactly equal. Through the mobility and all these adjustment, you can have that VDD by 2. But note that this will not work for, this will not be always VDD by 2 for different corners like slow, 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 fast, fast, slow, fast, fast, or maybe typical. All corner will have different results. So generally we have to do something that also we will take care of it. So inverter can be realized as a as a comparator. This is what our proposal is. The important part is comparator need to have the gain of 2 raised to n plus 1, right, where n is the number of bits. In our case, for our case, it will be 2 raised to p by n by p plus 1, the required gain, right? So single inverter cannot give you the required gain, so you can always have the cascade of such inverters, and you can have the required comparison with the required gain. And in parallel to that, you can have the delay block. As I told you, like at the beginning, you have to adjust it. So we'll not go into detail of that, but this is very important to make sure that every signal is reaching on time and exactly at the same way it is required. Anyway, so going to the next, as I told you that this particular inverter will give you problem in terms of the required comparison value. Like here, if I'm saying it's compared with VDD by 2, the normal inverter, if both the RON and ROP are exactly same, then this will be compared with VDD by 2, but over different corners of process. This is not going to be the same. It's not going to be VDD by 2. So what I recommend, and this is also from one of my old paper. So what I'm proposing over here is, let's have one common mode feedback, which is like this, right? And just concentrate on one side of that where biasing circuit is there, which is acting as a common mode feedback, where I'm connecting the body of first inverter to the output of the 3 cascaded inverter. You can make it 5 also, you can make it 7 also, no problem, right? Any odd number of things will work, but 3 are sufficient enough to have your requirement. So when you're doing it, you design these 3 inverters, you keep it over there, and let us assume that you have requirement of VDD by 2. You wanted to have the VDD by 2 over here by adjusting R1 and R2 exactly equal. If this is VDD by 2, this we are expecting to be VDD by 2 exactly at the same switching threshold. But if this is not going to happen, let's assume that if it's more than VDD by 2, then what will happen? This particular gate will act as a back gate. This particular so here you had VDD by 2, the requirement, and here there is something higher than what you were expecting. So this is acting as a back gate, and it will try to decrease other side. With respect to VDD by 2, it will be delta will be other side because of negative feedback topology over here, having 3 inverters, and because of going down, other side will be upside. If it is upside, other side will be down. So earlier it was going up, so that makes the negative feedback phenomena, and over the period of time, this particular loop is getting settled to VDD by 2. If you wish to have VDD by 2, it will stable at VDD by 2. If you wish to have something else, you can keep it that also by adjusting value of resistances, right? And whatever value is coming, just feed it over here to have the required V out of VDD by 2. So this is got you can achieve it through the common mode feedback circuit, and this is very simple circuit which you can use it to achieve the required low energy, right? And you can have the inverter based comparator, just add them back to back, right? So that you can have the required gain also, right? Okay, so here what we proposed is an inverter can be used as a comparator when switching threshold voltage is VCM. So it's not compulsion that you have the VCM to be always VDD by 2. It may be anything which can be altered by the value of resistances is one thing. And the best part is what we proposed is actually process independent. For any value of the process, any value of the voltage, or even including any value of temperature also, this will give you the same thing because it's a ratiometric thing. So it will not give you any deviation. So common mode feedback circuitry for fixing the VCM across PVT is possible, right? And when you have the input offset voltage requirement can be achieved by chain of inverters in cascade. When you're doing it, it's not the normal thing. We can use it. You can use the Sutherland approach. You can have the logical effort, and you can have accordingly the tapered design, which is going to give you better results in terms of gain, better results in terms of bandwidth, right? And better results in terms of its speed. And of course, as I told you, like delay block is required to just to make sure that chain of inverter is giving you the output exactly on time when you have other side is also available. So you are not, you have to match that. If it is not in sync, then output will be different. Now these are the results on 28 nanometer, right? So different results we looked at, and if you look at that, without bias is my without CMFB, and with bias means with CMFB. You can see that there is a large variations. IUC variations means input offset voltage variation is there, and we design it for 14 millivolt. If you look at that, so everything is in across the corner. We made it less than 14 millivolt, right? And here you can see that how much voltage is we got it. So noise margin high, low, and all these things have been achieved. For histogram also, it has been checked that how much variation is there, and it's within the half LSB, which was requirement of 14 millivolt, right? So same has been checked for various things, and it gives the result. We look at the just this comparator with various comparator available in the literature. It gives very good energy efficiency, right? And that will be like can be used in our hybrid structure. So now the next point might be like you can use the segmented charge scaled ADC. So the CDAC converts this digital input to an analog voltage, and the CDAC decides that various things like SNR, INL, DNL, but INL is actually the most important thing, which is going to give you the required non-linearity. So we generally make sure that various things are there. Inherent sample and hold circuit is there. There is no static power consumption should be there. We are using the bottom plate sampling so that you avoid the parasitic effects. You can have the capacitance spread of deck, which is increases with the number of bits. You can have the lower switch resistance so that you can achieve the required speed. So all these things are the standard one and which you are using generally, right? So let's look at the structure. So normal structure will have 1C, 2C, 4C, 8C, 16C, 32C. So all the times it's actually multiplied by 2. It's a binary weighted CDEC structure, but this is conventional CDEC structure will give you lots of problem when you have the charge available on 32C, because this is acting as an MSB, and others are actually connected to 0, and there is a location of input where it's VDD by 2 plus 1 LSB. That is a location where that becomes 0 and other becomes 1. So they don't become 1 and 0 just like that. It's coming, and 1 and 0 will be having the the large spike over these capacitances. So, and you don't have time to get it discharged also. So you cannot achieve the required or the possible, the error, which is only half LSB, which can be guaranteed. Or if you want it, you need to make, arrangement like that, so that you can achieve the required things. So these switches or these glitches has to be, less than half LSB. So what proposal is the simple one, which is also given in most of the books. This is called segmented CDAC. If you go to any company or anywhere where they are using the DAC, that's actually segmented, where it's a combination of binary weighted plus thermometric code. So MSB array, it's lower 4 bits can be binary and upper 4 bits might be thermometric, and then later on it can be converted to, the binary. So that will give you advantage in terms of achieving the required, required resolution and required non-linearity, and INL and DLL will not be impacted too much. Now let's look at that. So this is again, when we are doing this, when you have the MSB array and LSB array, earlier it was like going with 1C, 2C, 4C. It's a binary weighted. For having 6 bits, you are getting almost like 32C bit, or multiply by this, you require 64C, right? That's the capacitance you require. For this case, it's not that much. It's actually only 8C is coming from here, and rest of them are around 4 and 4. So 8. So 16C are only required here. So there is a huge reduction in area. Other than even in switches also, you have to have, the smaller switches, because you are not driving the big capacitors like 8C, 16C. You are now only driving C. So that way also it's advantageous. So effectively you are reducing lots of area. You are reducing lots of capacitance spread, increasing speed, and requires only simple switch circuit. You don't require to go with very complicated things or maybe very high value of WIL. So when we did with that and we looked at that, we found out that still after, exactly VDD by 2, still this INL is actually increasing, right? If you look at that carefully, this is not the regular design which was giving you, only. So allowed thing is plus or minus 0.5 LSB, right? So this is what we are expecting, that to have good ADC in a working mode, you must have, the error or the non-linearity with respect to code within plus or minus 0.5 LSB, which is not in this case, first of all. And of course, you can see that beyond this half point, even though we took the segmented, it's going up. This is one observation we took it so that we can improve it, right? And other things we checked for its performance in terms of input output code, in terms of transient response, in terms of frequency response, and we also check the dynamic range, effective resolution bandwidth, jitter, and its power consumption and all these things. Of course, DAC is taking the highest power consumption because of its large number of array and having that segmented structure. So if you're taking something else, then this will be drastically a big number. Anyway, so going further and looking into the PYD evolution, note that this also having the same inverter based comparator and plus segmented CDAC. So this is what has been used, and you can see that you can have the required results. And as the whole design is actually inverter based, the whole design, if you look at the design, which is actually inverter is actually just a digital block. So if we can check that if there is an inverter based thing, if you change this VDD, or you can alter with digital logic high and digital logic 0. So we check that what is happening. So we first look at its VDD, we change it, and we looked at the frequency, how much frequency we can achieve. So the highest was available was 1 volt, but we applied from 0.5 to 1 volt, and check that what is the frequency we are achieving. We are achieving something in, going in hundreds of megahertz to gigahertz, but there is a, one zone, efficient figure of merit zone, where you are achieving good FOM and high frequency also. So that zone can be used for some computer architecture thing also, where you need to have efficient energy is required while transferring the data. This is one thing. Other than that, you can have the looking into PVT variation for all our results in terms of input offset voltage. Even same way, when we are looking VDD with respect to the SNR, SFDR, you can see that that gives very flat result. If you know that SNR is equal to 6.02 N plus 1.76, so where N is the number of bits, or you can say it's ENOB, effective number of bits. So approximately 6 times N is the requirement of SNR. So if you are having the 36 dB, by the way, SNR is measured in dB. So if you are achieving 36 dB of SNR, means you are having approximately 6 bit, right? So you are achieving 6 bits thoroughly from 0.5 to 1 volt, right? So exactly with this equation, when you feed it over here, you can see that the required number of bits are achieved, and the FOM is also pretty good, right? Now we looked at DAC, we looked at comparator, right? One can also take care of the SAR structure, because one observation we made it over here, and we kept it for later understanding, that after VDD by 2, the code of, like, if there's 6 bits means 64 number code, exactly 32 code is exactly equal to VDD by 2, right? Or you can say it's 1 and all 0, and later on all these uh, all these uh, unwanted things are happening, means it's keep on increasing, you see. And my even segmented is also not able to fix it properly. So what we can do is, instead of looking into thermometric to binary, so here the code is available with thermometric code. And till now we were converting thermometric to binary, and then we were giving that to the DAC. Even the output which we were getting to this DAC, the digital input was binary. But if we are not converting, or if we do not want any kind of binary conversion, then we can directly go with the thermometric code also. So this is what we did, that instead of making a binary weighted conventional CDAC, let's make the thermometric weighted switched CDAC. Means you have all the capacitors equal, and also other alteration has to be done in terms of input buffers and all. You can do that. It's similar structure, but you are dealing with thermometric code now, not binary code, which is going 1 and 0 only in binary fashion, but this is thermometric code, which is going with the transition, where only one place it's going from 1 to 0, and rest of them are either 0 or 1. So we again did the calculation on paper, and we found out that the E total, or the energy total, which is required in the structure, is 25.81 CV square, where V is the reference voltage. In our case, it might be common mode voltage. So accordingly, you can find out. And we checked with various structures available in the literature, like conventional one, monotonous one, split EDC, two-step, 2-bit step, and this work, which is actually thermometric to binary, which is giving me the energy efficiency of something like 25.81. Of course, monotonous has, lower than that, or even 2-bit step is near to that. But why should I care about it? Because this is my requirement for my thermometric to binary, and which is consuming pretty low energy comparing to conventional or maybe even segmented. And you are comparing to this one, which is the reference, you are having the reduction of energy to be 69.03%, and that was significant. And the capacitance wise, when we are doing it, because this is also important part, I'm only getting 56 times Cu, whereas here, which was giving me the lower energy, but area was high, and area is actually money, right? When you are in VLSI, so uh, making the trade-off, even it's, I would say it's better for my application, and area saving is also significant in this case, where we are winning. So we did the tap out. This is the microchip photograph. We did it in 130 nanometer. This has been tested with various instruments in IIT Delhi. So we used clock generator, function generator, and with the active probes on oscilloscope and logic analyzer, it has been checked, right? And this whole ADC was consuming something like 550 by 540 micrometer square of area. And when we check the measurement results, now look at this. This is not now simulation. This is not simulation. This is the actual ADC which we tapped out. And when we looked at the results, gives us very promising result. Means let's observe at 32, and beyond that, it's being staying in plus or minus 0.5 LSP. This is good news because we used our own thermometric 2-binary coded CDAC, right? And that gives us good results, right? So this is good part. In DNL also, it's within plus or minus 0.5 LSB. The SNR or SFDR for a given frequency, or even if I'm increasing the frequency, the SNDR is actually remaining same, more than 38, which tells us that you are having more than 6 bits of performance. So comparing to previous FOM with various papers published in TVLSI, TCAS2, ISCAS, and again TVLSI for various nodes, because here the major part is, we are using 130 nanometer. If you are using this technique in lower technology node, you can achieve even much lower figure of merit than this one. So 195 femtojoule per conversion, that is what we achieve, and comparing to others, it's very low, right? So this is the thing. And note that all the comparison ADCs are the measured results. Nothing is simulation, right? So this is what we learn it. Now, what like we are going little ahead of that, which we also filed a patent also for that structure. Earlier structure also got patent. So going further, which is actually important one, what we are saying is, if you have p number of comparators in parallel to realize flash, and when you have the thermometric code, I know that thermometric code will be always, on the transition, you will see 1 and 0, right? So that's the overall concept of thermometric. So wherever you see the transition, that is what actually creating, the, the decision. So what my proposal is, if you have such 7 segments to realize 3 bits, so this is for 3 bits of realization, and you have 7 comparators, 7 DACs, I'm going to look at this transition only and make sure that only 2 are on, rest of them are power off. These are power off. Only two are on. All DACs, all comparators which are actually in parallel, we are going to make it on. We are going to make it off. Only two which are in between are getting on. So that will save lots of power, right? So this is the very simplest way to save the power. So we did that, and that makes all other circuitry going in off mode. This is just a looking into the power aware. We call this one as power aware ADC, where for a given input, we are saying that there is transition. Wherever transition is there, you're going to make only those comparators on, or two comparators on, right? So this is a working flow diagram, and every time you have to refresh it with the VDD, and VDD ground has to be switched off. We again, tapped out, which took around 0.43 mm by 0.49 mm of area, and this was the layout of that. It requires lots of area on CDEC array, lots of area on comparator array. But as I told you, like only two comparators and two DACs are going to be on. Rest of them will be off, right? Just it has to be tracked that which two comparators are getting on and off. So that needs to be checked. In power aware ADC, this is post layout simulation. And we found out that this is again like this is power aware architecture. If it is one, means you are reducing the power. So because of reduction of that in comparator, in SAR block, and in CDAC block, you are getting reduction in power. And by the way, this is with the worst case condition, right? This is not designed with the best case where you have to have the power is actually reducing, but we are changing the input from 0 to VDD just to check the maximum output. So this is a sine wave with going from 0 to VDD, where you can have the worst case results, and in that also we are getting lots of improvement in terms of power. It has been checked for various process corners, and SNDR, SNR are achieving the required number of bits, which is SNR equal to 6.02 n plus 1.76. Means just you have to look at the 6 times n approximately, which is going to give you the SNR. So around 33.8 dB, which is just a little bit less than 6 bit, right? So this is what you are achieving. And looking into total power, we achieve something like 5.27 milliwatts of power for gigasamples per second of ADC with 6 number of bits, right? And that can be visible over here. It has been compared with state of the art based papers like TVLSI, TCAS2, and it has been seen that this work is giving 119 femtojoule per conversion, comparing to the previous one, which was consuming 195 femtojoule per conversion step. This is again like very like significant amount of reduction is possible to see, right? Around the 76 femtojoule is reduced comparing the first one. So it's going in a correct direction. The only thing is like we are in 130. I looked at many other also like who are achieving very low like 119, but that is because of they are using low technology node. So if you are applying this to smaller technology node like 3 nanometer, because this particular technique is inverter based, where most of the things are digital, and there is a promising that lower technology node will have a the lower power consumption, and effectively you can have the better energy efficiency. So this is what you can achieve. Now one more thing we can do. So what we found out till now, that there are various comparators in parallel, various DACs in parallel, right? You just shut off some of the like some of the comparators and DAC has been switched off. So effectively there are only two comparators at the end and two DACs. So through that we got an idea, which also have been filed for patent, that why don't you just, if there is V in star is sampled V in. If you have V in, comparison part which is coming from DAC, let's make it, dynamic such that, so here for for 6 bits you have 2 raised to 6 number of compartments, right, going from 0 to VDD, right. I'm saying through power aware, I know that which part is moving, which two comparators are there, means I know that only at the front side I need to switch on, like for this case it's 8 bit, by the way, right, 3 at the input. If there are the 3 bits of p bit you are getting, means there are 7 comparators, and if you are making only one place of transition, it's effectively 3 bits of effective number of bits coming in a cycle. So that might be advantageous over here. So that is what we did, and we kept only two comparators with varying these two. Means earlier we were comparing input with various labels, right. Now what we are doing is wherever input is there are two other inputs were there, right. Here two inputs, you actually change it from outside and reduce it till the point you will get output near to this point, right. Once you get it, or once you are near to that particular point, then there is not much changes. Understand, if this is for transceiver application, but if it is sensor application where there is no abrupt changes in analog quantities, like if there is a 27 degree of temperature which needs to be converted to digital, next temperature must be like either it's increasing, decreasing, right, 28 degree, 29 degree, or maybe 26, 25. There is no abrupt change. So if you found out where your level was, means you found out here and here, then the changes are not pretty fast. This is an assumption here. Sometimes it goes fast also, by the way. So if it is not going, then you can find out this and go till the LSB. Means every single clock cycle you have the output, because this input is changing by a bit by 1 LSB, which is equivalent of 3 bits of resolution in flash. So it's not exactly 1 LSB on total scale, but that is 1 LSB at the P side. So that gives advantage, and you make the so much of the decision making voltage. Just you move that and you find out that what is the output, 1 and 0. So that will give you the digital code, and you are not changing here any comparator, anything. We call it the tracking one, the structure. And as we have only two comparators at the input side, this is a fractional bit, right. So this gives you something like 1.65 bits, because of that 2 raised to n number is required to have your n number of bits. For with this two comparator, you will have 3 different compartments. So 3 compartments will give you effectively something like 1.62 bits only. That literature people are calling or approximated to 1.5 bits. So this gives you 1.5 bits of structure. So that's why I call this one as 1.5 bits of structure with 2 comparators, 2 DACs, one SAR and one digital to digital converter. I'm not going to now use any other things because this is thermometric and other side is binary. So I'm going to use the my code, which is going to give me the required results. So this is also part of that patent, where how to get the best results, which will be giving us the energy efficient output, right? Now going further, so these are some of the results, how it's moving and how you get the results. And this is the whole structure where not only that CDAC and other things are getting the input, but there is something called track control. Track control is the one which is finding out what output is required from, some of the given inputs. So this has not been used with the AML structure, but this can be extended for that, and that is what actually going on, to have the track control, which is going to give me the required reference from CDAC, which is near to the input side, right? So that way you can have the required uh, digital output, which is thermometric in nature. You process it with successive approximation digital logic, have the output, and let's convert that digital to digital using my code. That will that is part of this, again another patent, where we got these structure, we tapped out. This is taking similar area, similar things, and we got some of the switch capacitor array sampling and other things. You can see it's similar area only, and of course it has been designed so that we have minimum number of parasitics, and many things have been taken into account for designing such a layout. So this is fully uh, full custom design, looking into again like PLS results. So it's a post layout simulation results, and we did it with the 1024 points of FFT. We're getting the required results. We check with the PVT, SNDR, SFTR, all these things have been checked, total power, and it has been compared with the state of the art work. Note that we achieved 119, before that 195, right? So 195 femtojoule per conversion step, 119 femtojoule per conversion step, and then we are achieving. There are two results are there. One is with the worst case, and one is with, once you have the stable output, the best achievable figure of merit, it's 79 femtojoule per conversion cycle. So that has been checked, and that has been uh, taken into account for uh, checking the validity of our results. So these are the structure. There are many things happen after that, but we'll stop here with these structures. So making the conclusion on that, considering the timing and all, will make the conclusion that ADC architecture is improved using the combination of flash ADC and SAR ADC. The comparator optimization is performed using the novel inverter-based comparator, which is actually PVT independent, voltage scalable. This is the best part of our design, where the whole thing is digital. You can even design it using some automated tool if it is required, or if it is becoming standardized. Low power consumption, higher operating speed. We have achieved 3.22 times reduction in switching energy on paper for switched CDAC. We achieved 27% of reduction in overall power consumption when we tapped out. Multi-featured on-chip configuration, we got it. The frequency synthesizer also designed, but which has not been shown over here. So that also have been designed for that transceiver structure. Scope might be like, if you like this work, then one can make ultra high speed ADC with sampling rate beyond 10 GSPS. By the way, we were targeting for 100 GSPS with. So this work was with one of my collaborator from TU Berlin. So he gave me this idea, and I worked on it, and thereafter we got the results. And later on, like only work done by me, and later on, like he was not part of it, but we started with that. So he gave me this idea to make something for 100 GSPS. So this overall ADC was much beyond 1 GSPS, because that was only one structure. But I made the time interleave structure so to achieve 10 GSPS. But going beyond 10 GSPS is actually difficult. So one can make beyond 10 GSPS, which will give you the high performance optimal communication, high performance measurement systems, 6G communication systems. You can have MIMO system, and of course, you should not restrict yourself to flash plus SAR. You can also make the combination of pipeline, delta sigma, SAR, and many others. Like, so you can have the better performance, the hybrid ADC. So other than this, one can also make hybrid TDC. So it's time to digital converter. So not only analog to digital converter, which is going to have with the hybrid structure, but you can have with the hybrid structure of TDC, and which can be investigated for space and biomedical applications which require such structures. You can also have hybrid ADC, DAC, TDC, DTC performance can be evaluated under gamma radiation. So this was the major work came from one of my PhD student who graduated in 2022. So I would like to thank SMDP C2SD, because that was part of it, and all the chip tap out happened from SMDP C2SD, so Ministry of Electronics and Information Technology, and some part was also from Digital India Corporation. We got it Young Faculty Research Fellowship, so through which I used that part for tapping out some of the chip, and also Professor Shari Chatterjee, who gave us facility for VLSI Design Laboratory to test our chips. Thank you from my side. Thank you all. Professor Anu. Hello.
Yes, sir.
Yeah. So any doubt, any question, if you have, then we can have it.
Yes, sir. We have a few questions in the chat box. People with more queries, please ask your doubts in the chat box itself. We have, which is the popular ADC architecture used in commercial applications?
There is nothing like perfect. All ADCs are being used, all structures, right? It depends on the application. As I started with the transceiver application, right? So if you are saying that if it is a mobile application, then of course you need to go to pipeline, SAR. Those are the architecture. For low speed applications like biomedical and other sensor applications, you should go to the sigma delta, right? In same way, like you can also use integrating type ADC. So that is actually taking longer time, but it depends on your application and or the requirement of the conversion cycle and requirement of your figure of merit.
Okay. Sir, can you please highlight the importance of ADC in transference?
Sorry. Hello.
Yes, sir.
Yeah. Can you repeat your question?
Can you please highlight the importance of ADC in transceivers?
In transceivers. Okay. Look,
Yes.
everything you want to be used as digital, right? So if you want digital, what you are talking is actually analog, right? So if you are want to send something on digital side, of course you need to convert it to digital, and that is possible only with the ADC. In same way, it's a receiver side also, you are receiving the signal, so that side you need DAC also. So DAC and ADC are equally important for a given number of bits for the required bandwidth. Does it answer your question, Kashvi?
Yes, sir. If there are any more questions, please drop them in the chat box. I think we're done with the questions, sir. Thank you so much.
Okay. Thank you all. If you want, like I sent already my presentation to Dr. Anu, so she can share with you if if you wish to have that. Okay. Thank you all.
Thank you so much, sir.
Okay, so I'm leaving, right? Is it okay?
Yes, sir.
Okay. Okay, thank you all. Thank you, Dr. Anu and other organizing member. Thank you.
We kindly request all participants to fill out the online feedback form, the link for which has been shared in the chat box.
So Kashvi, can we request all the participants for a good photograph?
Yes, ma'am. All participants are requested to switch their cameras on as we'll be taking group photographs.
So we request all the participants and we will give the rights also. Please give rights to everyone so that they can switch on their cameras. We request all the participants so that we can have a group photograph. Thank you, everyone. Yes. It is wonderful to see everyone online and actively attending and participating in this 6-day online ATAL FDP. We request the coordinators to please click photographs for our dear participants, and this will go into our records. Thank you so much. And we would also like to hear from some of you in person. So we can see a number of you are attending our program on daily basis and sharing your questions with our speakers. So can we hear it from any of the participants? You can just raise your hand and perhaps we can start the interaction. Kashvi, please invite one by one. All professors are there. Industry participants are also there. I request Kashvi to please, start inviting one
I
by one.
can see two hands raised, ma'am.
Yeah. Please start with Mr.
Yeah,
Joydeep Kundu. Yeah, please invite him.
I can see Dr. R. Mithili, ma'am's hand raised.
Yeah.
So, ma'am, we would like to hear a few words from you.
Yes, ma'am. Can you all hear me?
Yeah.
Yes,
Good
ma'am.
evening, ma'am. How are you?
Yes, ma'am. I'm Dr. Maithili from KIT, Kalingar Karnataka Institute of Technology, Coimbatore, Tamil Nadu. Really,
Yeah.
it is a wonderful session, ma'am.
Yeah. We are not able to hear you. I mean, just unmute
Can
yourself. Yeah. Now,
yes, ma'am. Yes, ma'am. I'm Dr. Maithili, ma'am, from KIT, Kalingar Karnataka Institute of Technology, Coimbatore, Tamil Nadu. So it's my pleasure to share my views about the ATAL FDP AACT sponsored titled Advances in Semiconductor Technologies from Fundamentals to AI-Driven VLSI Design and Packaging, organized by North Cap University, Gurugram. Actually, all the sessions are well structured and well informative session. So I would like to thank the entire organizing team for giving such a wonderful session to us for the past 5 days, and especially all the resource persons too, Professor Muralidhar Miriala, Dr. C. Ramachandra, Professor J.P. Singh, Professor V.V. Rao, Mr. Shubham Jain, Ms. Nikita Gulia, Dr. Vinay Budraja, and the session which was taken previously by Dr. Hitesh Shirmali. So all the sessions are very much informative, and they have provided industry relevant insights and recent technological trends which enhanced all of us to understand the modern semiconductor ecosystem. So overall, the FDP is timely, relevant, and impactful. So once again, I thank the entire team for giving such a wonderful opportunity to all of us to attend this FDP in the right time too. So thank you all.
thank you so much, ma'am, for your kind words. And
Thank you.
dear participants, this is our second opportunity to organize ATAL FTP 6-day in online mode. So your feedback and your comments have been very valuable in improving the conduct of this program, as we have got the second opportunity. And we look forward to reading all your feedbacks and improving next time also. So thank you so much, ma'am. And
Thank you, ma'am.
Kashvi, yeah. Kashvi, please invite the next professor.
I now invite Mr. Joydeep Kundu. We would like to hear a few words from you, sir. Thank you.
Yeah, so I think we are not able to hear. So perhaps we can, request Dr. Satnam Singh to kindly share his valuable feedback and comments. Please give mic rights to Dr. Satnam Singh. He's been waiting.
I've
Yeah, good
given.
afternoon, everyone. I'm audible.
Yes, sir.
Yes, sir.
So, first of all, kudos to the organizing team. You have, the sessions were well planned, and the whole program is, the need of the hour, like the semiconductor. We even our government is focusing in this area, and I really appreciate the effort which were, put in by the organizers, and all the sessions were planned as accordingly. All these people, they attended, and from my side, It's 5 star. Thank you.
Thank you so much, sir.
Thank you,
And we
sir.
could really see in every session some of the very interesting questions, as our speakers has also shared, were raised by you. We could, we can recollect your questions in the chat box in every session. So thank you so much
Thank you,
for
ma'am.
being
Thank
an
you.
active participant. So we would like to share that, we have a number of participants. So there were 389 registered participants, and we could see that 200 plus were active every day. And the area of expertise is also very diverse. So we have people from physics background, we have from mechanical background, and mechanical strength is also there. So we can see, we had sessions on manufacturing, packaging, etc. So we request more of you, more professors to share their feedback. Uh, please feel free to raise your hands. We will give the mic rights to you, and please feel free to share your feedback. Yeah, I think this is it. So
Yes, I think we're done, ma'am.
yeah. So thank you so much, everyone. So rest of the, comments and feedback, perhaps we'll take from your feedback forms. Yeah. So we can see one hand raise from the 4C Tron Bangalore ID. So we request sir to, please kindly share his feedback or any kind of suggestions for us, or any kind of motivation will also really help us. Sir. Sir, your mic is, it needs to be unmuted. Aryan, please unmute this 4C Tron ID. Aryan, can you unmute 4C Tron
Yeah.
Bangalore? Yes,
Now,
sir. Now you are
can you?
audible.
Okay, good. I could not attend all the lectures. However, my colleague, Dr. Ramachandra, who works in Forcitron as a technical director, handling semiconductor, gave 2 lectures. And also I could see I'm IESA member. I'm active in semiconductor for last 40 years, including solar. Ramachandra and myself are colleagues 40 years before to manufacture first silicon wafer monosilicon in India in 1983. Probably forgot to mention this during the session. However, now we have grown a 12-inch monocrystal sending one of my colleague who worked in Siltronics for 8 years to China, and we have grown successfully 12-inch crystal, which can be monocrystal for semiconductor solar. Now we can transfer the technology to any company investing in ingot growing, number one. Second thing is the session on the clean room given by Mr. Singh, or it went on first 10 minutes about the clean room. It was good introduction, but it deviated to the equipment level. What I mean, you have to address a clean room properly from the design stage, installation stage, and its supervision and validation. It's a big 10% of the semiconductor industry cost is hidden, or 10 to 15% clean room. If the clean room is not properly designed and operational, and it is not maintained properly, and all the chip what you make, all the wafers you handle is waste. Suppose the yield goes, Ramachandra explained that yield is also a parameter. Therefore, yield depends on the clean room condition. We built a clean room 25 years back at Sitar, Bangalore, a DRDO organization today, and also Indian Institute of Science, CNSC, is an example that clean room is still working even after 25 years. We are associated with the Felcon company in UK. We are back in India now as a Felcon India. If any of the IITs, NITs, or any industry, or any of your professor working in this industry are interested in the clean room, please contact Dr. Ramachandra or me personally. We would like to contribute our expertise, transfer it to the young engineers. And I'm happy that North Cap University is organizing such a good seminar with a good audience. And I'm happy that at this age, I'm attending this with interest as a student. Thank you very much for your effort.
Thank you so much, sir. And Professor Ramachandra, and we got to know that you were also very active. So we had Professor V.V. Rao also, our own Professor Swaran Ahuja. So all senior professors, we are really thankful for your motivation and consistent, presence with us during our all ATAL programs. We are really thankful, and
One more
participate.
request. Next session, I would like to introduce one guy from UK who has worked in 50 years and who built the clean room in India 25 years back. Probably we'll talk about wet benches and wafer processing along with Dr. Ramachandra. And also on the clean room, we can put another expert from Jaydev, who worked in Bell for 40 years, who is also in my group. We can share this as three people: in-God growing, clean room, in-God growing, wafer manufacturing, and chip manufacturing. A session by 3 will address online. If any time is given, we can participate for the benefit of students and professors who are interested. Thank you very much for taking your time. Thank you. Very good.
Thank you. Good day, sir. And thanks to all the participants. And our next session will start around 6 p.m. So we will take a small break.
One more request. I would like to get the lecture delivered by IESA member about the semiconductor boom, because I missed that due to some other occupant.
No, she will be delivering it around 6 p.m. only, sir. So Dr. Rakhi Nangia is there from ISA.
Oh, he's delivering late. I thought the session is already over.
No. The session is there.
Oh,
so due to the professional commitment, so some adjustments were needed to be made. So she is there around 6 p.m. We will inform you, and we will inform all the participants.
Thank you very much. Good day.
Okay, thank you everyone. So we will start around 6, and we will float this information with you through the chat box and in the WhatsApp group also. Thanks again.
Your feedback is extremely important to us and help us enhance the quality of future programs. We kindly request all participants to fill out the online feedback form, and the link for which has been shared in the chat box. Thank you. We now move on to session 12, and it is an honor to welcome Dr. Rakhi Nangia. Dr. Nangia is the Deputy Director at the India Electronics and Semiconductor Association and serves as a semiconductor fab policy advisor to the Ministry of Electronics and Information Technology, Government of India. She has played a pivotal role in the formulation of India's semiconductor fab policy, stakeholder consultation, scheme frameworks, and appraisal of proposals under national semiconductor initiatives.
Hi everyone. Okay, so I'm sharing my screen. So just let me know whether it's visible to all of you or not.
Yeah, screen is visible.
The screen is visible. Okay, let me do it in PowerPoint mode. Okay, it's in presentation mode, ma'am. Yeah.
Yes.
Okay. So hello everyone. So whosoever the audience is, so means my greetings to all of you. So let me start with my presentation because we have a limited time. So my slides are too much and I need to cover a lot. Okay, so coming directly. So I would be speaking regarding the semiconductor market. As you all must be knowing that it is a very booming word nowadays in the market. Everywhere it is being talked in industry, in academia, in government, at global level it is being talked. Okay, so we will talk about the global and domestic market of semiconductors and what are the potential opportunities in this area, right? So whosoever have a query, so as Pooja ma'am suggested me, you can type in the chat box and we can take it later. If the audience would be able to speak, so my first question was like, in a daily routine, means how many electronic devices usually a person use. So I think on a daily basis, we used at least 10 to 15 devices, electronic devices, and every device nowadays have a lots of chip inside. So starting from a simple headphone, earphone, laptop, mobile, your TV, fridge, your smart, any like Alexa or whatever you can call it, a modern car. So all of these has hundreds to thousands of semiconductor chips. And I think nowadays everyone who is present here better know like what is a semiconductor chip. So a modern car, for example, have nearly 2000 to 3000 semiconductor chip in inside. So that's why it is so much means fully automatic car and nowadays fully automated home. So nowadays semiconductor is everywhere. I think I can hide this. Yes. Yeah. Okay, so this is a simple flow like what I am talking about of a semiconductor chip. So how a semiconductor chip is going to be manufactured, right? So it starts, the journey starts from a sand, like a simple sand, but this is a simple sand, but not in that form, but it's a very purified form is being used to make the silicon ingot of that. So this cylindrical shaped silicon ingot then being diced into various wafers, and those wafers like the electronic circuit or semiconductor circuit we can say, that is being fabricated on that wafer, and then these wafers are cut into individual chips, and then individual chips are being packaged into complete like IC. So this is the complete flow to manufacture it. But as it is looking as simple here, it's not completely not like that. It's a very, very, very complex process that I want to tell you. Most of you may be knowing it, most of maybe some of you don't know this. So but it is a very complex process, it's a very technology intensive, very cost intensive industry. Okay, so this slide maybe I should I don't know who's I think I can avoid this slide as well. It's just showing that like what is the total electronics market of India. So the four graphs are showing the domestic production, how much is the demand. So 179 US billion dollar is the total electronics demand, and out of that I am coming directly to the next slide. So nearly 110 billion of semiconductor ICs are being used domestically, means the Indian demand only is means by 2030 it would be 110 billion US dollars, and the global demand would be $1 trillion. So nearly 10% of the global demand is being means is of India only. So from this graph, I want to show that by in 2020, the semiconductor demand, or I can say the semiconductor market, was $15 billion in 2025, and as we are in the 2026, so it is somewhere around $65 billion. And by 2030, the semiconductor market of India itself would be $110 billion. It is estimated with a CAGR of nearly 22%, right? And you all must be knowing that what I show in my first slide are the demand drivers, means where these chips are being used. And it is on the demand of only chips, not the raw material, means the equipment, the gases, the chemicals. it's not included, and it is the market of only chips. So what are the various demand drivers? Are you are using smartphones, you are using a lots of wearables and hearables, you are using various like modern vehicles. Similarly, data centers means compute, data storage. A lot of data is being used nowadays in mobile. You see your smartphones means how much is the memory is there. Similarly, in the all the telecommunication like IoT and 5G, etc. So every electronic device are using these type of semiconductor chips. So because of the usage of semiconductor chips in every electronic devices, so that's how the market of the semiconductor chips. So now my second question to the audience is, okay, the the market of semiconductor means the demand of semiconductor in India only is 110 billion by 2030. But how much is India manufacturing as of now? So I don't know means what are the answers are, but let me tell you. That India as of now is not even making a single chip. Okay, so every single chip is being imported by other countries, and in other countries, who are the major ones can be seen in this slide. Okay, so US is the number one, then South Korea, Japan, Europe, Taiwan, China, and then rest of the world. So these are the major countries who are like fulfilling the demand of the globe, including India. So US alone is supplying 50% of the global demand of semiconductor chips. Then coming to South Korea, it is serving nearly 19 to 20% of the global demand. Then Japan, Europe, including Germany, etc., they are catering to 10% of the global demand. Then Taiwan, then China, right? This is the semiconductor supply chain. So by this slide, I would like to make you understand like what are the how it is being fragmented. Okay. So if there is a chip in your hand, or if there is a chip in your any of the electronic device, so what are the various segments through which a chip is being manufactured? Okay, so first of all, a lots of research is being done, research and development. So there are many research firms like IMEC Belgium, A-Star Singapore, and lots of SCL in India. So lots of research is being done. Then the chip is being designed. So I think my arrow is visible. So this block is showing like the chip is being designed in a fabless company. Then the chip is being fabricated in a foundry, like we used to call it semiconductor fab. Then after when this wafer get fabricated, it is being packaged in a ATMP facility, or we can call it as OSAT facility. Okay, and when through these phases, design, fabrication, and assembly, there are various inputs which goes into, like for designing, various EDA tool and core IPs are used. For fabrication, a lots of semiconductor manufacturing equipment that means off the line as well. I can take these questions. So lots of equipment like lithography, etching, processing equipments are being used to fabricate a chip. Similarly, various chemicals, gases are used to fabricate a chip. Then the individual ICs are being assembled and packaged in an OSAT unit. So I mean to say that if these were the various countries, so how many types of companies would be there because of the so many segments to design and fabricate a single chip? So this slide shows like what are the type of different companies in different segments to completely manufacture a semiconductor chip. So what are the different segments are? Number one, the companies who make IP cores, intellectual properties, the companies who used to design EDA tools to design a chip, the companies who are manufacturing specialized materials which are used to fabricate a chip. Similarly, various wafer fab equipment companies who used to provide the semiconductor equipment like lithography process equipment to the semiconductor foundry. Similarly, fabless chip companies means the design companies who used to design the chip. We usually call it like VLSI design companies, like. And what are IDMs? Integrated device manufacturers means who used to do all these above works in their means by themselves only. So IDMs are the companies who start from the design, who fabricate, who package as well, right? Then the chip foundries means who only fabricate the chip. So these are the various verticals in this pyramid, like IP cores, EDA tools, materials, wafer fab equipment, chip design companies, and foundries. These are the various examples of the companies. Means some of you may be knowing there are various companies, semiconductor companies. So Synopsys, Cadence, Mentor Graphics, ASML, Applied Material, Apple, AMD. So these companies work in different segment of this market. So this is the complete chain of the semiconductor chip manufacturing, and different companies work in different segments of the semiconductor. Okay, so a few logos all of you know very well: Google, Apple, Facebook, Amazon, Huawei. So these are the Tesla. So these are the various companies who used to use these semiconductor chips in their products. So when these products, final products are, it may be like this jet is showing here in the diagram. So a jet nearly uses 5,000 of number of chips in it. Similarly, a modern car, similarly your phone or iPad or anything, right? So these are the end products. So these companies are usually called OEM. So when chips are manufactured by these companies, then these companies use these chips into their products, but the OEM companies make use of those products into the final products. These are the world top 15 semiconductor companies, you can say by sale or revenue. So all of you must be knowing Intel, that is the first one. Samsung, TSMC, SK Hynix, Micron, Qualcomm, Broadcom, Nvidia. So these are the top 15 semiconductor companies, and most of them you must be knowing are from US. At least 50% of those are from US. Others like SK Hynix is of Korea, TSMC is of Taiwan. So similarly, so that was the purpose of showing that slide, that demand is there in India, but none of the company as of now is manufacturing a chip, and most of the chips are being manufactured by 7 or 8 prominent countries, and rest of the world means nearly all together rest of the world is making 1% of the demand. So I am skipping this slide. This is somewhere means this is the number of fabs worldwide, like how many fabs were there in Taiwan, how many semiconductor fabs were there in US, etc. These are the top 10 semiconductor equipment suppliers. So as I just mentioned earlier, that in a semiconductor foundry, lots of semiconductor equipments like lithography, photolithography, EUV lithography, processing, vacuum evaporation machines, etching machines, a lot means nearly 65 types of semiconductor equipments are being used in a semiconductor foundry, and these are the prominent companies who are making those equipment. So number one is the first three are the Applied Materials, ASML, Lam Research, Tokyo Electron, KLA. So out of those, out of these 10, again 3 are from US. These are the IP and EDA tool companies. So VLSI design students of BTech and MTech must be knowing this, because they used to do various designing in their curriculum as well. So though they must be using Synopsys, Cadence, Keysight, and Siemens EDA tools. these are the OSAT companies. OSAT means, as I mentioned, when the electronic circuit got fabricated on a semiconductor wafer, then those chips are being cut into individual ICs, and then those individual ICs are being packaged by OSAT companies. So these are the example of OSAT companies, means who used to package those chips. So in packaging, Taiwan, Korea are ahead of US. So because my purpose was to show all of you that what is the scenario right now, right? What is the global scenario? What is the domestic scenario? So till now I was talking about the global scenario. I told about like what is the domestic demand, what is the global semiconductor demand, which are the top countries who are serving those demand, and which are the top companies which is catering all the demand. So till now I was talking about the global ecosystem of semiconductor. Now I am coming to domestic. So as I was just mentioning that as of now, India is not manufacturing a single chip. All of these are being imported. But it's not like that India can't do that. India is now progressing in that direction. The reason being, a lots of demand is there, and there is a lots of government push to set up this semiconductor ecosystem in the country. So we were having it in bits and pieces, somewhere a little bit of manufacturing capacities are there, few international companies were there, and India is a powerhouse in terms of VLSI design. I am very proud to say this, that nearly 20% of the global world design engineers are Indians. Means if in a company or in a means global semiconductor design engineers, the demand, if let's say it's 1 lakh, then 20,000 engineers would be Indian. So India is has very strong presence in terms of semiconductor design. But the challenge is that as of now, India is designing for international countries. Like we don't have that IP in our country. The intellectual property is of a multinational company. For example, Intel is there in Bangalore, AMD is there in Bangalore and in other cities as well. Similarly, Micron has their centers in Bangalore as well as in other cities. Similarly, Marvell has its center in Noida as well as in Gurgaon. But they are all multinational companies which are present in India, and they are using Indian talent to design their chips. So the chip, uh, we have the talent, we are designing the chip, but that IP is not of India. Okay, so IP remains of any international company. Okay, but at the right side, I would like to show that domestic fabless companies. So nowadays, many companies have started designing chips. So the Sankhya Labs, Sturdian, Kiral Systems, Signal Chip, these are the various startup companies who are designing the chips. Similarly, equipment and tools companies, for example, Applied Material, Lam Research, KLA, all three are US company, but they have a strong presence in India, right? Similarly, EDA tools company, Cadence, Synopsys, Mentor Graphics, ARM, all three are US companies, but they do have presence in India. Okay, Mentor Graphics is of Germany, definitely, but Cadence and Synopsys and Keysight, they are of US. In the manufacturing sector, where is our presence? So there is one strategic fab, SCL, that you must be knowing in Chandigarh, Mohali. Similarly, GATEC is present in Hyderabad. Sitar is again present. It is a lab of DRDO again. There is CDIL, which manufacture discrete semiconductors like thyristor, transistors, MOSFET, etc. in discrete form. So it is again present in Mohali. So with this slide, I want to show that India has an ecosystem, but as of now, it is emerging. Okay, so yeah. Similarly, 7 state-of-art nano-fabrication facilities are there. All we used to heard various IITs and ISC. So they are working in this direction, and they have a nano-fabrication facility in the premises. I think if NCU students are here in the seminar, so they must have gone to IIT Mandi. Similarly, in IISC, IIT Mumbai, the nanofabrication facilities are present, and students as well as faculty can do hands-on, and a little prototyping of semiconductor chips are being done here. I think I can skip this. So this is our presence in terms of the talent. So many universities, IITs, triple ITs, NITs, so much of educational ecosystem is there, and there is lots of government programs for skill building there. For example, electronic sector skill council, INUP is again a program of government of India to support the nano fabrication units in different IITs and IISc. And similarly, SMDP or C2S program, I think the NCU BTech students of semiconductor design must know this program. So it is again a very supportive program for educational institutes to get the EDA tools, and so that students can do hands-on practice. This slide, with this slide, I wanted to show you like at which nanometer nowadays global companies are working. For example, TSMC and Samsung, they are working at 2 to 3 nanometer node size, and the cost to set up a foundry goes to nearly 20 billion. So that node is not here. So I have listed a 5 nanometer. To set up a 5 nanometer semiconductor fab, the cost to set up a semiconductor foundry is nearly 12 to 16 billion US dollars, and it is a huge amount. So that's why I was saying that this industry is very much cost intensive, and similarly very much technology intensive. So to support this, Government of India has launched Semicon India program of nearly 10 billion US dollars, and government is providing support to the industries who are coming up with their technology partner to set up semiconductor fab, display fab, compound semiconductor fabs, etc. in the country. So means a little bit of domestic ecosystem is there. On the other hand, government is giving the push in terms of incentive, in terms of support as well. Not only incentive means money is one part, but government is also giving various types of support. For example, there are various schemes who are supporting the tools, who are supporting the not only central government, state governments as well. They are coming up with their policy under which they are giving subsidy on the land on which semiconductor fab would be manufactured. Similarly, they are giving subsidy on power, because in a to run a fab, a huge amount of power is needed. Similarly, they are giving subsidy on water, because to run a fab, not normal water but ultra pure water is needed in millions of gallons. So that support is also available through state government. So what I mean to say, um, that a small ecosystem was there already. With the government push, now the ecosystem is being built. So I think I can skip. Yeah. So yes, coming to So this is a very important slide, as I was mentioning the Semicon India program of Government of India. So as of now, 10 projects have been approved, which are setting up their semiconductor fab or OSAT unit in various states of India. So the figure and the picture is showing 10 projects which has been approved by Government of India, out of which 6 are ATMP projects. Okay, so the investment may not be very interesting to you, but for the industry, these numbers, like how much is the investment, which company is doing, is very interesting. The biggest project is by Tata Electronics. So they are investing 91,000 crore to set up the semiconductor fab. Similarly, Micron is there, who is setting their assembly unit and investing nearly 22.5 thousand crores to set up the OSAT unit. Yeah. So as I was mentioning, that Government of India has invested nearly 10 billion US dollars. So this is something with which we can compare, like how much there is a global race nowadays, which is going on. Every country is investing so much into semiconductors, because it's like means no one wants that others should win. So they are investing a lots of. For example, US has invested. US has in India there is Semicon India program. Similarly, US has come up with CHIPS Act. So they used to call it CHIPS Act, and nearly 52 billion US dollars they are investing. South Korea, they are investing 450 billion US dollars. So this is something to understand the global scenario, like what countries are doing to means to be self dependent in this ecosystem. Nice. And similarly, China, they are also investing 150 billion US dollars in to set up the semiconductor industry. However, it is the after US, China is also the big in semiconductors. These are the recent fab related announcement. TSMC is a company of Taiwan, but they are investing a lots in Arizona to set up their additional fabs. Similarly, Samsung, which is a company of Korea, they are investing 1.3 lakh crore in Texas. Intel, which is they are again, Intel is a US company, and again they are opening 2 fabs in Arizona. Global Foundries, they are opening up a fab in Singapore. SK Hynix, which is a Korean company, they are again opening another branch in Korea. Yeah. So I think this slide should be interesting if if students are the audience. So as I was talking about the talent, okay. So a lots of fabs are coming. Similarly, a lots of push is there from the Government of India. Investments are flowing. Various international companies are coming to India and investing in India to set up their unit in India. But there is a lots of talent crunch. As of now, it was there, it is there, and going forward, if the steps would not be taken, then a lots of talent crunch would be there in the semiconductor industry. So this we can take in a positive way. So here there are lots of opportunities. So as one of the article, the sector is scaling quickly with 40,000 new semiconductor job postings recorded in 24-25 alone. So this number is not small. Only in a single year, there were 43,000 around number of job postings in semiconductor sector. And by 2030, the country's semiconductor workforce was projected to expand by over 120% to nearly 4 lakh professionals. Means by 2030, 4 lakh professionals would be needed only for this industry. And so there is a lots of talent crunch as of now. So according to an estimate, by 2027, there is likely to be a shortage of 250,000 to 350,000 qualified professionals in the fields of semiconductor. including fab, packaging, design, manufacturing, R&D. So this is again an article, Talent Crunch Looms Over India's Semiconductor Industry. So if there are students in the audience, so you can take it as an opportunity, and NCU has launched BTech in semiconductor design and manufacturing. So you can leverage that opportunity. So with this, if the time permits, I want to open another document. Ma'am, please tell me if there is 5 minutes of time.
Yes, we can sum it up. You can take 5 minutes and then
Okay.
yeah.
Yeah. So whether my Word document is visible?
Yeah, it's visible.
Okay, okay. So this I didn't put on the slide because this is something quite like lengthy thing. So with this document, I would like to share there that what are the gaps to set up to bring the semiconductor, means to develop the semiconductor talent pipeline and in India, and what are the solutions. So for, number one is manufacturing and process engineering talent. So what we are missing, because we don't have any expertise of usually in colleges and this thing, these topics are not being taught: lithography, yield engineering, and if it is being taught, then only at the like theoretical level, but most of the things are not at the hands-on basis. So most graduates are usually design or software oriented but not factory oriented, because a lack of hands-on practice is there. And the problem cannot be solved alone by academia, because there is a lack of hands-on fab, there is lack of equipments, yield data. Various gaps are there. So industry and academia has to work hands in hand to solve these type of problems. So I have just mentioned what may be the potential solutions. Fab embedded degree track may be there. Similarly, there may be adjunct faculty from fabs, like the employees who are working in the fab may come up and can teach the process modules, etc. Similarly, there may be other government funded program to build this gap. So similarly, there is a list. If it is needed, I can share it offline, and anyone can go through this. Like, what are the gaps, and what is missing, what is critical, and what are the potential solutions that can be worked on. So that's it, ma'am. That's it. I was like preferring to show.
Thank you so much, Dr. Raki. Devika and Kashvi, if there are any questions, I would request you to check the chat box.
Yes, ma'am, there is a question.
Yeah.
What is the impact on startup or business due to open design with RISC-V based SoC and boards for application like agriculture and healthcare?
Can you please read the question again?
Yes, ma'am. What is the impact on startup or business due to open design with RISC-V based SoC and boards for application like agriculture and healthcare?
Okay. Okay. So a very good question, first of all. Here I would like to share that there is no risk. There is no risk, because there is so much demand, even since when there were licensed tool, like licensed softwares, and these things were used. And even after like coming up of the open source tool, everything is working on, and means every open source as well as licensed tool are being used. So there is no risk on startups, because there is limitation. The open source tool has their own limitation. So whosoever finds like means their application or their utility must be served by that tool. So if that is not being served by the open source tool, then they will go for the license tool. So there is not such kind of like a challenge for the startups who are coming up with their license tools. Anything else?
I think we are done, ma'am. Thank you so much.
Okay, so thank you so much for giving me the opportunity, Pooja ma'am and the team. And thank you so much to the audience as well to listen patiently. Thank you so much. And you can reach out to me through Pooja ma'am or someone, whosoever wants to have something more.
Thank you so much, Dr. Rakhi. Thank you taking out a time from your busy schedule. I
No
know
problem.
you had been occupied today with lot of other
It's a
activities and you took out time on our request. Thank you
no
so
problem,
much
ma'am.
and
Thank you.
to be
It's my
part of our
privilege as well.
FDP. And I hope there are many many participants are still having the questions, but I would request the participants, since Dr. Jerry, our next resource person, is already here, we should
Right.
not be running late.
Yes, yes.
So we can start with the next session. And if there
Sure.
are any questions, just write to us. We will forward it to Dr. Raki and let you know the answers, whatever possible. We can do it for you. And thank you so much, Dr.
Okay.
Raki.
Thank you. Thank you, ma'am. Thank you. I'm leaving
So,
with your permission. Thank you.
okay. Thank you so much. Dr. Jerry, can we start with the next session?
Hello.
Yes, sir.
Yeah. Good evening to everyone.
Yeah.
I'll just
Devika,
share my
yes, sir.
screen.
You can meanwhile share your PPT. They will, student coordinators, they will just introduce to you to our participants.
Okay, hold on.
Yeah, Kashmi and Devika, please start.
We now move ahead to welcome our next speaker for the day, Mr. Jerry Enriquez.
Mr. Enriquez is the business unit head at Sahasra Semiconductors Private Limited, with extensive experience in the semiconductor industry.
He has been closely associated with semiconductor business operations, strategic planning, and ecosystem development, and brings valuable insights from an industry driven perspective.
His work focuses on understanding industry requirements, market evolution, and the practical challenges involved in building and scaling semiconductor capabilities.
In this session, Mr. Enriquez will share his industry perspectives and insights, highlighting the key developments and observations from the semiconductor sector.
We encourage participants to actively engage and post their questions in the chat box. A brief Q&A will be taken at the end of the session.
With this, we warmly welcome Mr. Jerry Enriquez to kindly begin his session.
The chat box will remain open and a Q&A session will follow the talk.
Hello, do you see my screen?
Yeah, it's
Yes,
visible.
ma'am.
Yes, sir.
Okay, let me start my pitch for this evening. So this will be my flow of discussion. Brief introduction of semiconductor business trend, semiconductor business in India, evolution of semiconductor packages, future of semiconductor packages, and this is a bonus discussion. I'm going to share with you the secrets of success in semiconductor. Okay, so I'll just give you a brief introduction. I took a ECE at St. Louis University, Philippines, 1993, and was hired by Texas Instrument in December 6, 1993, as a cadet product engineer. And I went to TI Houston in 1995 as a product engineer for network business unit. And in 1998, I was elected as member technical staff by TI. And I handled NBU CDSP HDD product engineering in 1998. I completed my MBA in 2003. and I became the TI Baguio Test Development Manager in 2007, as well as covering product engineering in 2010. And I retired from TI in 2014, and I moved to OnSemi in the same year as test new product introduction engineer or manager. I'm responsible for the QFN bring up in OnSemi from Malaysia in 2015. And I headed the QFN operations at the same time the test development and product engineering management for OnSemi in 2015. And in 2024, October, I was hired by Sahasra Semiconductor here in India. Now my work-life balance, non-negotiable outside work, family, of course, facilitating leadership seminars, farming, fun of playing golf, reading leadership self-improvement books, and cooking. Okay, so let me start with a brief introduction of semiconductor. So it starts with silicon. And why silicon? Because this is the second most abundant element on Earth, and it has the highest melting point, and it has a low band gap energy of 1.1 EV, and so on. It can be doped with different impurities to create N-type or P-type semiconductors. So once we process the silicon, we form it with ingot for wafers, and we form them on wafers. We cut this ingot and form into individual wafers, either 6 inches, 8 inches, 12 inches. Then we build them in terms of packages, ICs. So this is the evolution of semiconductor packages. It started with a dual inline package or DIP, and that was my birth year. Now maybe in 1970s includes QFP, SOP, LCC. Then in 1980s, pin grade array, PGA, and 1990s also we released BGA. And year 2000s we had this QFN, CSP, system in package, package on package, WLP, and 2.5D integrated circuits and 3D integrated circuits. I'm pretty sure that this is your birth years in 2000s. Now I just have to point out that dust is a major factor affecting our semiconductor site, and we measure the dust particles daily. And this is the specs of our front of line assembly area at 10K, end of line around 100K, and test area around 100K. This is the semiconductor supply chain. These are the key players in industry. So I start with the design, then followed by the electronic design creation of these circuits. Then it will go to wafer suppliers or wafer builders. Then these are the equipment suppliers as well as the raw material suppliers. So we have two sets of suppliers, equipment and raw materials. Then on the manufacturing equipment supplier, we have these front end suppliers. So these are the different suppliers as well as the back end suppliers here. And we have separated test equipment consumable suppliers as well as the equipment suppliers and OEM. And on the below left are the different manufacturers of ICs, including fabless, foundries, OSAT, and IDM or integrated device manufacturers. Now for the value chain, these are the key players. So we put it in a different perspective. We have the suppliers, These are the different key players. These are the third one is the second one, or in the middle is the semiconductor device industry. So these are the semiconductor manufacturers and also the tech players. These are the um, customers, and at the same time, they are the one who supplying the system. Same with this one, but this is in terms of revenues. As you can see here, that the semiconductor device industry is a little bit higher in terms of revenues. This is the wafer fab market share. So as you can see here, that the trend is on 12-inch wafers, the one that I mentioned a while back. 12-inch wafers. So the orange one, the red ones, the blue ones. In China, that is the red one. Korea, that is the blue-green ones, etc. So that is the trend right now, having a 12-inch wafer and 8-inch wafer. And this is the end application revenue distribution. And this is the trend, AI driving next phase revenue growth beyond 2030. So AI will be playing a key role in shaping up or shaking up semiconductor. These are the AI end markets. And for the next 5 years, we will be expecting growth, humongous growth in servers attributed by the AI, as well as some growth in automotive industry, which is the highest one. So this includes the EV from China. So we are using ICs on our EVs. So for the existing packages that we released worldwide, so this is the QFN lead package, which is the what we call matured packages released to each customers. So this is the QFN, quad flat no lead. Why no lead? Because it has no foot, just the metal pads are embedded on the package. For LGA, this is the land grid array package, and this is commonly used for RF modules, sensors, etc. And also this BGA, initially this was used for our servers and as well as some cell phones during the Nokia days, and as well as the Ericsson days. And this is also the flip chip, in which we will do a underfill. And this is also for GPUs, CPUs, AI accelerators, RF devices. This is a low resistance package, and it has improved thermal dissipation. SIP is the system in package, in which this is a integration of multiple semiconductor dies into a single package. So it has a different, in the picture below, you will see here that there are some LDO or low dropout module, PMIC processor, and also this standard packaging for molding. And this is widely used for smartphones, wearables, IoT devices. This is the Internet of Things, RF modules, etc. MCP is the multiple multi-chip package in which you will be integrating two or more semiconductor dies of similar or related function. And this is commonly used for logic plus memory dies. This is used also for mobile devices and also consumer electronics and embedded systems, as well as some memories. WLCSP. So it's a wafer in which we put bumps in a wafer level. So this is the wafer level chip scale package, and this has no molding or packaging, and commonly used for smartphones, wearables, Internet of Things, sensors, RF chips, and PMICs. And for the future packages, we have this panel level packaging. So initially we have been building wafers. Now it will be on a panel um, package, and we will be using interposers or connectors, and this will improve the density of one panel or one some sort of one quantity as we go up, or as we go bigger. Then we will be improving our area efficiency at 81%. Also, the chip on wafer on substrate or CoWoS. So this is the CoWoS in which you will be also using interposers, as well as for HBM application. This is a high bandwidth memory. And this will improve the capacity or the functionality of one IC. Other one is a chip on panel on substrate. So similar to the SCOWS, it has a same floor plan. It has a 4 HBM, and you do this packaging using the interposer, in which you'll be doing the interconnects between the RDLs, as well as the some dies on the IC. Now for the latest process technology, I'll be sharing one on assembly and one on test. We are building wafers. Initially, when I started the discussion, I mentioned specifically that the wafers are built using silicon. Now, in this case, we are seeing some wafers with low-K material handling, and it will be difficult for normal manufacturing processing if we encountered such low-K material during wafer dicing. So what we introduced was this laser groove process, in which we do a laser grooving on the left and on the right of the saw street. Then from there, we do remove the middle using laser groove, and we do the normal mechanical saw, in which the saw will only cut the silicon part of the wafer. So that's for the assembly trend right now. And we are using this on one of our one of our uh, product, eSIM. And the other one is this, initially we are doing singulated test process in which a test, here at the test, we test units one by one or in parallel, maximum of like around 40 or 30 units per insertion. Now we have implemented this strip testing, in which a test we will do testing on one strip of lead frame simultaneously or in parallel. So this will improve your throughput like around 16x, depending on the size of the lead frame and the density of the lead frame. Any question so far? Hello?
No, sir.
None? Okay. This part, I will be needing a participation from the audience. I will be sharing with you secret of success in semiconductor. These secrets, I have experienced them while I was in semicon, and these secrets also of success can be applied in your career, in your personal life. Okay, so I recommend or I suggest the audience to write down these items because these are secrets. Okay, so the number one secret is having a positive attitude. So in semiconductor, we will be needing a lot of positive attitude. One of which is, anyone from the audience, what does a positive attitude means?
Sir, optimistic attitude.
Yeah, optimistic, correct. What else? Any more? It's also an attitude of gratitude in which we count our blessings. Every day or every moment in our lives, we receive small packets of blessings, and if you combine them, then it will become big wins for us. So that is an attitude of gratitude, and that is how are we also encouraging our team to develop this secret, having a positive attitude. One question: what is positive about traffic jam, or if you have been jammed in a traffic? Anyone?
Maybe learning patience, waiting for our turn to come. Taking
Yes.
rest, someone has said taking rest.
Yeah, taking rest. Yes, exactly. So if you are jammed in a traffic, then it's also an opportunity for you to take a rest, and at the same time browse your cell phones if there are some urgent messages from close relatives or friends or family members. Then that is no recognizing the blessing on any given moment in any situation. Okay. Now the second secret is vivid imagination. What is vivid? Hello?
Like a strong clarity.
Yeah, crystals, crystal clear, very clear. And if you have a very clear imagination, then that's where you will become more successful in your lives. And who wants to have a car? I mean, who has a goal of having a new car, or yeah, new car? Anyone who has a goal for having a new car? Well, if
Yes,
you
so
want,
people have raised hands and they're giving thumbs ups.
oh, yeah, sure. Please go ahead. Yeah, I cannot see the persons raising their hands. But please, uh, you can guide me. Who will be the? Oh, so you can guide me. How many people are raising their hands? Because in in coming up with your goals, you should have a very vivid imagination, wherein
So
you just not mention only plain car, but also what car is it, half or full? Because there are some cars who are half, like pickup or sedan that is full. Do you want it big or small? What color? Yellow, blue, black, white? Do you want your car to have curtain so that it will protect you from heat later on? Do you want some entertainment in your car? So you need to have at least a 6.1 entertainment system or Atmos entertainment system inside your car. So these are specifics that you need to have in your imagination so that you will have very clear, crystal clear in your goals or in what outcome you want or what results you want to become. And my uncle said, my uncle said before that, imagine, can you recite this one?
imagination is more important than knowledge.
Yes. Imagination is more important than knowledge. And I believe that because everything in this world is created twice. One, first in the mind, then second it becomes a reality. That's why imagination is more important than knowledge. Okay, and to prove you that, or to have, we'll have a small exercise for this one. Okay, this is the dots. This is the rule. So we have 9 dots here, right? Do you see the 9 dots? So the rule here is connect these 9 dots without lifting your pen or pencil and without crossing a dot twice. Anyone who wants to try? Want me to show the solution? Once, going twice. Okay, so I'll give you the solution. This is the solution. This is the, oh, sorry, this is the line, then going here, connecting this dot. Then go straight here. Sorry, I'm not good on my, because I'm using here and here. So what does this mean? Do you see this area? Anyone seeing this area that I highlighted?
Yes, sir.
Yeah,
Yes,
so
sir.
this is the outside thinking out of the box, because the solution of this exercise is not within the box but outside of the box, and these highlighted areas are outside of the box. So even in semiconductor, you have to think outside of the box so that you create solutions, you create fixes, and you create innovations in semiconductor. Did you get everyone get this one?
Yes, sir.
Okay. Then the third secret is the written goals. Written goals is being smarter, smarter. S starts or S stands for specific. So you should be specific in your goals. M is measurable. So if you want a goal like I want to be attractive next year or in December 2026, then that is not measurable. It should be measurable always. Like I want to see myself weighing 100 or 75 kilos or 65 kilos by December 2026. That is measurable. Or I see myself depositing this much of INR, like 5 lakhs by March 2026. Then that is measurable. A is attainable. Attainable in semiconductor, you will be based on some computed theories like capacity or like UPH. Then that's where you create your goals in semiconductor, in which it should be attainable based on theory. It is based on data. At the same time, it should be realistic based on the computed information of the on the machine. And also T is time bounded. Time bounded is I can give you an example. I want we I see myself shipping two two 2 million units next year. Is this time bounded? Is it time bounded? next year or next month or next 6 months. It is not time bounded, because next year, by the time that you reach 2027, year 2027, then that next year will be 2028. So it should be a specific date. Like I see myself shipping 2 million units on or before June 15, 2026. Then that's the time that it will become a time bounded and also exciting. The moment that you get scared or you get scared in achieving your goal, then that's where you get excited, because that will keep your adrenaline in achieving your goal. And lastly, rewarding. It should reward yourself that after shipping or after achieving this goal in your semiconductor, then it will be rewarding for us that, okay, the customer will be satisfied, there will be good customer satisfaction. Then that's rewarding for everyone, not only for you, but also for the operators, as well as the technicians, engineers, and it should be rewarding. Okay. And another secret is stay focused. So you focus on your goal, because in your goal, in the middle are obstacles. If you focus on the obstacles, then your goal will be not clear. But don't focus on your obstacles, but focus on your goals. Because once you stay focused on your goals, then your obstacles will be not that clear, and at the same time you can easily overcome these obstacles. And lastly, take action. While you have written your goals, take action. For me, what I did was, when I want to have a new car, then I took, or I drew I drew a drawing of a car on our bathroom mirror, so that every morning that I wake up, I can easily see the drawing of that car. Then it will come to my mind, and oh, it will remind me of my goals. Same thing with Semicon. If you want to see some good innovation or good results or output, then you have to put it in your bulletin board, or in your personal board, to make it visible to you every morning. That is the first part. The second part is take necessary actions to achieve that goal. Like, for example, in semiconductor, you need to ensure that machines are in tip-top shape, the raw materials are fluid, or their arrival will be on time, no delays, etc. So that is the last secret that I like to share with you. Okay. Okay, I guess that ends my presentation now. Um, can I share with you another file?
Yes, sir.
Okay, hold on, hold on, hold on. Hold on. Do you still see my screen?
Yes, sir, I am able to see it.
I think I already opened this one, but somehow I cannot find it on my. Hold on for a while. Hold on. Do you see now my screen?
Yes, sir.
Yeah, just wanted to share with you our company, Semiconductors, Sahasra Semiconductors. So this is the first operational OSAT here in India in terms of wafer processing, IC packaging, and IC testing. So just as a snippet of this, that we have 7 operational facilities here in India. Oh, 7 operational facilities, 6 in India and 1 in Africa. And this is the market capitalization of around more than $200 million. And we have 9 sales offices spreading across India, UK, Europe, America, and Africa. And we are exporting to 20 plus countries. And our workforce is around 650 employees, 25% are women. These are our different, this is the Sahasra Group snapshot. These are the different plants we have. And the semiconductor plant is here in Biwadi, in Rajasthan. This is the semiconductor plant. And in terms of our plant, this was started up in 2023 in terms of operation, and it is it is having a land area of 8,200 square meters, and the building area is around 6,000 square meters, and our clean room, the 10K or 100K areas, is around 4,000 square meter. This is a 1.5 hours drive from New Delhi, and the total plant capacity is around 60 million units per year. So this is on assumption of 1 die is equivalent to 10 wires. So this is our plant by zooming, and this is the 10K. The machines we have at front of line. This is the class 10K in terms of particles. So these are the different machines, as well as the end of line. These are the different machines. including testing. We do testing is for us to segregate or to test good units and segregate rejects and sort the good units or prevent that these rejects from being shipped to customer. So that's the main purpose why we are doing testing. And we also have our FA or reliability test tools like X-ray, ROIS. So that's where we do analysis before we proceed processing our materials to the next process log point. And this is the equivalent services that we perform here in Sahasra Semiconductors. This is the full stack and this is the value added. So this is what I have mentioned a while back, that this is the special process capability of our site, wherein we can process low-chem materials. This is the process capability that we do in terms of custom packaging, labeling, laser marking, tape and reel, etc. This is the plant capacity on our phase 1 area for specific IC type, and this is the packaging model. So for non-flash memories, we have a capacity of 5 million. Power driver ICs, that is around 20 million per year, and eSIM ICs, that is around 20 million. This is our application and timelines in building these different products in our facility. And in terms of memory, so we have a micro SD memory in production, and eventually we will be doing UDP packages in Q1 2026. That is the trial production, and third Q 2026. This is the mass production. And all of our substrate packages comply to the environmental requirement of our customers. So this is our process flow for this specific device or this package micro SD. And this is also for eMMC. This is the BGA that we will also planning to bring up in the next quarters to come. This is the process flow that we have defined, as well as this memory storages. So this is a SSD, USB flash, micro SD, DDR, etc. And for the SOP, this is the LED. These are the different product groups or products that we are building right now in production, as well as being qualified for production. This is also our package portfolio in terms of the timeline that we will be releasing these different packages in the near future. This is our DFNA. This is our package roadmap. As what I have mentioned before, that this will be our package roadmap for our site. And also this is the manpower growth targets. And for our supply chain, so we are getting our supplies locally and external India. But we have a goal of having a made in India move, so that we can have all raw materials manufactured here in our country. Then these are the different certifications, and as well as our different uh, stepping stones for developing further our Sahasra site. And also this is our value proposition. So this is the phase 2 of our building. It is ready for occupancy or for expansion. And this is our outlook. So that's all that I have right now, ma'am. Hello?
Yes, thank you so much, sir.
Yeah.
If there are any questions, please post them in the chat box. There are a few. Does Sahasra conduct any training program on IC testing?
What's the question?
Does Sahasra conduct any training programs on IC testing?
Oh, yes, yes, yes. Especially, of course, because definitely yes, because me, myself, is a test guy, and I am also overseeing the personal training of our test engineers. So the answer is yes, we do. We perform training on our testing, memory testing, as well as this uh, LED testing, etc.
Okay. What skill set you see for opportunities in Sahasra?
What is skill set? Come again? Sorry, I didn't quite get the question. Can you repeat that question, please?
Yes, sir. What skill set do you see for opportunities in Sahasra? Like, what skill set does one have to have?
Huh. I mentioned to you the secrets for you to be successful in semiconductor. Then the skill set will be having a positive mind, an open mind, regardless of courses, it's either technical or non-technical. It depends on the position that we look for, but generally speaking, we look for people with positive attitude, as well as they are willingness to learn new things.
As Sahasra is expanding from basic packaging to advanced 2.5D 3D packaging, what are the biggest technical and skill challenges you face during this transition, and how can academic institutions help in preparing industry ready engineers?
That is a very good question. As a matter of fact, uh, we are we are buying a new machine that will support advanced packaging, like the one that you mentioned, 2.5D, 3.0D. Uh, we plan to do HBM or high bandwidth memories, and the challenges that we are facing is the skill set that we will be accepting, because right now everyone or not all are knowledgeable on this advanced packaging. So what the universities or the academic can help is that we can collaborate with us. We can collaborate with them, and at the same time we provide them the needed topics for them to understand during their studying period or college period. the basic or fundamentals of this advanced packaging, and we can do some OJTs here in our site, so that once we complete the OJT, then we can have as a pool of talents that we can hire eventually. We cannot hire them all, but at least we can hire the best persons who are fit for that function or for that role.
Okay.
Did I answer your question?
Yes, sir. What are reliability testing done after packaging?
What are the reliability testing done after packaging?
Yes, sir.
Yeah, several items like tin whisker test. We are also doing some because we have some customer requirement that we need to be in compliant with. So these are like temp cycle, thermal shock, THB. That is a uh, thermal bias testing, as well as some other tests like this autoclave or pressure cooker test. That also includes IR reflow. That is part of the or that is part of the pre-qualification stage using the customer IR profile.
Okay. I think that is all the questions. Thank you so much, sir.
Thank you too. Thank you too, Kashmi.
Thank you, Dr. Jerry. It was a wonderful session and very informative session. And thank you so much for taking a time for our FDP. I I would let the participants also know Dr. Jerry was not well, not in a good health. Still, he managed to come and gave us such an informative session to all of us. I really thank you from heart, and lot of thanks. And we will be connecting very soon for our BTech program to take it further at the Sahasra. Thank you so
Yeah,
much, sir.
yeah, Ma'am Puja. I see it as my purpose to conduct this talk because I
Yes,
want to share my experiences and my knowledge to everyone, so
right,
that at
right.
least I can share this information, and be they will become more inspired in pursuing their goals.
Yes, sir. Our students are also part of this FDP. So I'm very sure Devika, Kashvi, they are all semiconductor students only. And they are inspired by your session today. And we will be connecting very soon to take our collaboration further, and so that we can propose some module for these students and take it forward.
Noted, ma'am.
Yeah,
Thank you,
yeah.
ma'am.
Thank you so much, sir. Thank you.
Okay, thank you.
Thank you. Thank you to all the participants for attending this 6-day FDP. Thank you, Ramakrishna sir. It is with our pleasure. Yet you are with us for all the 6 days, and I, and all the participants are requested to attempt the test. Uh, as already mentioned, it will be on the ATAL portal. So if there is any doubt, there is a YouTube video. You can go through that YouTube video and take the help, and you can attempt the test. And also a second thing, overall feedback is also to be filled on the ATAL portal. Once you have filled your feedback form, overall feedback form, you have attempted the test, you will be able to download your certificate from the ATAL portal. So all the tasks, these tasks are to be completed at the ATAL portal only. So please take care of this thing. If there is any query you are having, please, I would request you to email us on the ATAL FDP NCU at ncuindia.edu. We will be handling all our all the queries on that particular email ID only. Handling the queries on the WhatsApp is little difficult. So I request all the participants to follow the protocol and go ahead with the attempting a test and the feedback. Thank you, everyone. Thank you. We would love to connect with you, every one of you, in the future FDPs and the conferences which we conduct at the North Cap University. Thank you, everyone. Kashvi, we can end the session. Dr. Jerry, thank you.
Yes, ma'am. I'm going to
Yeah,
leave. I'm going to ask your permission if I can.
Yes, sir. Yes, yeah.
Okay.
We can leave.
Thank you
Yeah.
so much.
Thank you.
Thank you.
Thank you so much, sir.